Okay, Vy over Izz.
Sir, what about the web portions?
At point B, you don't consider the web.
Oh, okay.
Okay. Now, let's look at the white flange. Let's look at point A now. Okay, so point A, we know that. So this is shear stress at point A. It's going to be white flange analysis. All right. So it's only Q, right? Because the left and the right terminus are not related, is it? So that's why it's only what? Q. Okay. And then the thickness is equal to 0.2 inch. Okay. So the first moment of area that we're going to take is this area over here. Why this area? Because the terminal also always have the shear stress is equal to what? 0. Because the first moment of area at the terminal is equal to what? 0. Okay. And also, based on our analysis, the rules state what? The analysis direction starts from where? This is our analysis direction. Right? It starts from the where? From the widest region. I mean, furthest distance away from the centroid. Okay. Then from here, we want to find QZ at point B now. At point A. Okay. So the width is equal to 0.7. The depth 0.2. 1.5 minus 0.2 divided by 2. Okay. So this is equal to 1.5 minus 0.2 divided by 2 times by 0.2 times by 0.7, 0.196. Okay. Then from here, we are going to find the shear stress at point A. Okay. So the shear stress at point A is Vy over Izz. Right. So it's 0.196 divided by the Q is only 1, right? There's only 1 down here, right? So that's why this represents the Q. You don't need to write 1. I'm teaching, I'm writing so that you know. And the thickness, so this is the thickness now. It's equal to 0.2. Okay. So it's equal to 0.196. 0.196 divided by 0.2 is 0.98 Vy over Izz. So what we realize down here is the shear stress at point A is equal to shear stress at point B. Okay. So for now, we will be forced to find the shear stress at the centroid. Okay, because the centroid, the thickness is what? At the centroid, the thickness is 0.3. Right? But you have a bigger thickness, but you have more first moment of area. Okay, so now we have to find the first moment of area at point C. Now, for the first moment of area at point C, I'm going to do it 2 ways. We're going to do it from the top and from the where? Bottom. The answer has to be the same. Someone online has question. You guys okay?
One question, sir. Why do you have
Yes.
Why do you have 2 Q for the B and why do you have 1 Q for A? Can you please explain that?
At point B, right, is a what? Box beam analysis. The Q separate 2 ways from a terminal. Whereas for the white flange, the Q did not need to split. It's just 1 Q. Yes or no?
Yes.
That is why you only take 1. Okay?
Right, thank you.
Right. So next, we want to find Okay, do I have space? I got no space. We want to find at the centroid. Okay, so I'm going to, can I do this? Yeah. Okay, so now I'm going to paste this again. Now we want to find point C.
Sorry, could you please go to the previous page for a quick sec? I just missed the last bit.
Okay.
Thanks.
You're done, yes? Thank you.
Yeah, thanks.
Okay, so now we want to find what's going on at point C. Okay, so I'm going to do point C at both ways. I'm going to do the top. Okay, we're going to analyze point C from the top. Okay, so point C, and we also know that now this is a box beam analysis. Okay, so again we construct our shear flow. Terminal, so you have Q going one side, Q going the other side. You have to consider the whole area. Okay, so I'm going to divide the area this way. Where my ping is, we're going to divide the area there. Okay, so this is one area. This is the other area. Okay, so we're going to deal with box beam analysis now. Okay, so the Q at point C is equal to the width. Let me get the other image so I can see the geometry better. Width 1.4, depth 0.2, y bar is 1.5 minus by 0.2 divided by 2 plus, okay. Now we are looking at the web twice, the width is 1.5, no, the width is 0.3, the depth is 1.5, the y bar is 1.5 divided by 2. Okay. So this is equal to 1.5 minus 0.2 divided by 2 times 0.2 times 1.4 is 0.392 plus 1.5 divided by 2 times 1.5 times 0.3 times 2, 0.675. Let me see, 0.392 plus 0.675, 0.4, okay. So this will be equal to 0.392 plus 1.675, 1.067 inches to power of 3. So we can see that the first moment of area at point C is greater than at point B and point A. However, you have more thickness down here. So you have to find the shear stress at point C is equal to Vy over Izz, right? Now, because it's two, box beam is 2Q, and then the thickness is equal to 0.3. Okay, so it's equal to 1.067 divided by 2 because it's 2Q, and the thickness now is 0.3. So you have 1.067 divided by 2 divided by 0.3 is equal to 1.778. So you have 1.778, okay, Vy over by what? Izz. Okay. So we know that this is greater than at point A and at point what? B. Okay. So the next thing that we want to do now, I'm going to do the same. Now, we are going to take from the what? From the bottom. And I will encourage you all to do this also, because this builds confidence. Okay? If you don't do this, you will lose confidence. You will say, do I take from the top or do I take from the bottom? Okay? So confidence is very important in this topic. Okay? So confidence can only be achieved one way, by doing a lot of your homework question on your own. Okay? It's like Chinese cooking. Okay? For Chinese cooking, in order to make sure that it tastes well, what do we always put? Anyone? Oyster sauce. That's why whenever you buy Chinese takeaway from any restaurant, it all tastes the same, right? Oyster sauce, okay? So confident. I call it confident sauce, okay? Yeah, okay. Some of you say, Eugene, when you teach face-to-face, there's more bullshit coming out than anything else. It's okay. When I teach online, I'm miserable, no? As I say, it's just the screen, the toilet, and me, okay? It's miserable. Okay, so this is our shear flow. So you realize that this is a white flange analysis. Why it's called a white flange analysis? Because the left and the right are not connected at all. They are independent. Can you see that? Right? The left and the right are not connected at all. They are what? Independent. Okay. So for this case, the shear stress at point C or Q. So for this case, you only have Q, and the thickness is also going to be the same, 0.3 inches. Okay. So Q at point C is equal to, so I'm going to divide this way. Okay, I'm going to divide this way, one of my area, and this is my second area. Okay. So the width is 0.7. The depth is 0.2. Multiplied by 1.5 minus by 0.2 divided by 2. Okay. Plus, so that is the flange section, this section over here. Okay, this one is this section over here. And then the second one, the width is 0.3. The depth is 1.5 multiplied by 1.5 divided by 2. Okay. So the second one, okay, so this side belongs to here. Okay. So the equal, so 0.7 multiplied by 0.2 multiplied by 1.5 minus by 0.1 close bracket. So it's 0.196. Yeah, let me write better. It's equal to 0.196 plus 0.3 times 1.5 times 1.5 divided by 2, 0.3375. Okay. So 0.196 by 0.3375 is equal to 0.5335.
Eugene, I have a question.
Yes.
Don't we have to multiply with 2?
No, because the Q are not connected.
But there are two areas, like we are ignoring the left one then, didn't we?
You don't consider the left because the terminals are not connected.
Okay.
The terminals are not connected, right?
Yeah.
Right? Why we can close the top is because the first moment of area cannot go past the centroid. So the terminals are not connected at all. So that's why it's only Q.
Okay.
Okay?
Yeah.
The answer will be the same from the top and the bottom, right, sir?
Say it again.
The answer from the top and the bottom will be the same.
Have to be the same. If it's different, I'm teaching garbage. Okay, has to be the same. Seriously, it has to be the same because I show it to you mathematically already. Okay, so bear with me. It will be the same. If it's not the same, we pack up. So the shear stress at point C